One formation had everyone baffled, and people were saying, well, what is this?
For years, people dismissed crop circles as pranks and random patterns deliberately pressed into fields overnight. But in 2008, Italian inventor Umberto Baudo argued that certain crop circles encode precise geometric relationships, layouts that can be translated into physical systems designed to generate energy. That claim alone was extreme, but what made it harder to ignore was what he did next.
I think they're made by aliens or extra-dimensionals. I mean, it's a big universe.
He started building those systems in his own workshop, and if those designs actually work, then they wouldn't just be unusual machines. They would represent a form of energy technology that has never been publicly demonstrated, possibly one of the most suppressed ideas in modern history. The first claim. Baudo's idea only makes sense if you understand exactly what he was claiming and why it immediately puts him at odds with established physics. In any mechanical system, energy has to come from somewhere. If you spin a wheel, the energy comes from whatever force you use to start it. As the wheel turns, it loses energy to friction in the bearings, air resistance, and internal stress. That loss is unavoidable. Eventually, the system slows down and stops. This isn't a debated theory, it's one of the most consistently tested principles in science. Baudo's claim challenges that outcome directly. He argued that certain crop circle patterns encode very specific geometric relationships, ratios between circles, distances from a central point, and offset rotational axes. When those relationships are translated into physical components, they create a system where motion doesn't just continue, it increases under the right conditions. The key concept behind his designs is something called an eccentric rotation system. Instead of spinning perfectly around a centered axis, parts of the machine rotate off-center. That imbalance creates shifting forces as the system spins, and those forces can be redirected depending on how the components are arranged. In a typical machine, that imbalance would be a problem. It would cause instability, vibration, and energy loss. Baudo treated it as the solution. By arranging weighted components around an off-center core, based on the exact spacing he extracted from crop circle formations, he claimed the system could recycle part of its own motion. Instead of losing momentum steadily, it would reach a point where the internal forces begin reinforcing the rotation. At that stage, the machine wouldn't need continuous external input to keep spinning at high speed. The initial push gets it moving, but the geometry of the system determines what happens next. That is the part that conflicts with conventional physics. Because if a system maintains or increases motion without additional energy input, then either energy is being drawn from a source that hasn't been accounted for, or the measurements and assumptions behind the system are wrong. Baudo believed it was the first option. He argued that the designs extracted from crop circles were not accidental patterns, but precise configurations that allow mechanical systems to interact with forces we don't fully understand yet. That belief is what pushed him from analyzing patterns on paper to building physical machines in his workshop. Because at some point, the only way to test a claim like that is to stop talking about it and try to make it work. Unmeasured. Most people who study crop circles focus on how they look. They take aerial photos, compare shapes, and argue about whether the patterns are man-made or not. Baudo ignored that entire approach. Instead, he treated each formation like a mechanical diagram that had been scaled up to the size of a field. He started by isolating specific types of formations, ones with multiple concentric rings, repeating circles, and clear off-center placements. These weren't chosen because they looked impressive. They were chosen because they contained structure that could be measured. The first thing he focused on was ratios. He mapped the distance from the center of a formation to each outer circle, then compared those distances to each other. In several cases, the spacing followed consistent numerical relationships. When one circle was placed at a certain distance, the next wasn't random. It matched a proportional increase that repeated across different formations. That's what got his attention. If crop circles were just decorative, there would be no reason for those ratios to stay consistent across different locations and years. But if they were diagrams, those ratios could represent something functional, like gear spacing or rotational timing. From there, he moved to alignment. Some formations weren't centered perfectly. Smaller circles were placed slightly off-axis from the main structure. To most people, that looks like artistic variation. To an engineer, that looks like an eccentric layout, exactly the kind of configuration used to create uneven force during rotation. Baudo documented the offset of each component relative to the center, then translated those offsets into mechanical positions. He wasn't guessing. He was converting measured distances into physical placements. Next came sequencing. Certain formations contained repeating patterns that appeared in a specific order: large circle, smaller circle, gap, then another circle at a precise angle. When he mapped those sequences, they resembled the layout of rotating assemblies where timing between components matters. At that point, he wasn't looking at crop circles anymore. He was looking at instructions. To test that idea, he recreated simplified versions of these patterns using basic materials. Instead of crops, he used magnets and weighted components arranged in the same geometric relationships he had mapped from the fields. These early models weren't meant to generate energy. They were meant to answer one question: do these patterns translate into systems that actually move in a controlled way? When the components were arranged according to the extracted ratios and offsets, the systems rotated more smoothly than random configurations. When he changed the spacing, even slightly, the motion became unstable or inefficient. That result changed the direction of his work completely, because at that point the patterns weren't just visually consistent, they were mechanically sensitive. The exact positioning mattered, which is what you would expect from an engineered system, not a random design. That's when Baudo stopped treating crop circles as something to interpret and started treating them as something to build. And once he made that shift, the next step was obvious. He needed to turn those layouts into full-scale mechanical systems and see what would happen when they were pushed beyond simple rotation tests. From pattern to machine. Once Baudo confirmed that the geometry translated into stable motion, he stopped working with small test setups and started building full mechanical systems based on those layouts. Instead of copying entire crop circles, he focused on one type of formation that showed up repeatedly: a central circle surrounded by smaller circles placed at different distances, with at least one of them shifted off-center. That combination gave him three things to work with at once: a main axis, secondary rotating points, and controlled imbalance. He built the core of the system around a central shaft. That shaft acted as the main rotation axis, the part that receives the initial push. Around it, he mounted weighted arms positioned according to the exact distances he had measured from crop circle formations. Some of those weights were aligned symmetrically. Others were deliberately offset, matching the eccentric placements he had mapped earlier. That asymmetry is what made the system behave differently from a normal rotor. As the machine spins, each weighted arm experiences centrifugal force, pulling it outward. In a perfectly balanced system, those forces cancel out evenly. In Baudo's design, they don't. The offset components create a shifting distribution of force as the system rotates, and that shift changes how momentum moves through the structure. To control that movement, he added springs between key components. These weren't random additions. Their stiffness and placement were calculated based on the spacing between circles in the original formations. At low speeds, the springs stay compressed, keeping the system relatively tight. As rotation increases, the outward force stretches them gradually. That stretching changes the system in real time. The weights move farther from the center, increasing the rotational inertia. At the same time, the timing between components shifts slightly because the springs allow controlled delay in how each part responds to the motion. The result is a system where the internal forces don't stay constant. They evolve as speed increases. Baudo's claim is that at a certain point, those shifting forces begin reinforcing the rotation instead of resisting it. In practical terms, the machine starts behaving differently once it passes a threshold speed. Below that point, it acts like any other mechanical system. It needs continuous input to keep going. Above that point, the internal configuration changes enough that the energy required to maintain motion drops relative to the motion being produced. That's the moment everything hinges on. If the system simply becomes more efficient, then it's still operating within known physics. But if it reaches a state where it maintains or increases speed without additional input, then something else is happening, either an unaccounted energy source or a misinterpretation of the system. Baudo documented tests where his prototypes reached very high rotational speeds, thousands of revolutions per minute. As the speed increased, the outer components extended outward, exactly as predicted by his models. The machine remained structurally stable, and the motion stayed consistent instead of breaking down under stress. One detail he emphasized was temperature. In most high-speed mechanical systems, friction generates heat. Bearings warm up, materials expand, and energy is lost as thermal output. In his tests, he reported minimal temperature increase relative to the speed of rotation. That observation supported his claim that the system wasn't losing energy at the rate it should have been. From his perspective, that wasn't a small anomaly. It was the core of the entire idea. Because if energy loss is lower than expected while motion is sustained or increasing, then the system isn't behaving like a typical machine. It's either more efficient than current designs, or it's interacting with forces that aren't being fully accounted for in the model. At this stage, Baudo believed he had done more than interpret crop circles. He believed he had translated them into working mechanical systems that could be scaled into energy-producing devices. But that belief leads directly into a problem he never solved. Because building a machine that appears to work in your own workshop is one thing, getting other engineers to build the same machine and get the same result is something else entirely. The replication problem. At this point, the story reaches a point where most theories either hold up or collapse. Because once someone claims they've built a system that behaves differently from established physics, the next step isn't more explanation, it's replication. Can someone else build the same machine and get the same result? That's where Baudo's work runs into its biggest problem. There is no widely documented case of an independent engineer taking his exact designs, building them from scratch, and confirming that they produce sustained energy output beyond the input required to run them. There are no peer-reviewed papers verifying his results, no lab tests published with controlled measurements, and no demonstration where the full system is tested under conditions that rule out hidden energy inputs. That doesn't automatically mean the idea is wrong, but it changes how it has to be evaluated. In engineering, results don't become accepted because they sound convincing or because they work once in a single workshop. They become accepted when multiple teams, using different setups, can reproduce the same outcome and measure it in a controlled way. That hasn't happened here. Some people who looked into similar designs point to a few possible explanations for why the results appear unusual without actually breaking physical laws. One explanation is measurement error. If the system relies on rotation and moving components, it becomes difficult to accurately measure total energy input versus output. Small miscalculations in friction, air resistance, or stored mechanical energy can make it seem like the system is producing more energy than it actually is. Another explanation is delayed energy release. In systems with springs and rotating weights, energy can be stored temporarily and released later. That can create the impression that the machine is generating energy when it's actually redistributing energy that was already put into it earlier in the cycle. There's also the issue of hidden inputs. Even something as simple as vibration from the environment, slight imbalances in construction, or external electromagnetic interference can introduce small amounts of energy into a system. In most machines, that energy is negligible. In a finely balanced rotating system, it can affect how the motion behaves over time. These explanations don't prove Baudo was wrong, but they show how easily a system can appear to do something extraordinary when all variables aren't fully accounted for. At the same time, there's another side to this problem. Baudo claimed that even small deviations from the exact geometric ratios caused his systems to fail. If that's true, then replication becomes extremely difficult. It would mean the design has almost no tolerance for error, and even a slight misalignment could prevent the system from behaving as intended. That creates a situation where if others fail to replicate it, it could mean the design is flawed, or it could mean the replication wasn't precise enough. From the outside, both outcomes look the same. That's why this part of the story matters more than any simulation or prototype video. Because without independent verification, the claim stays in a kind of limbo. It's not confirmed, but it's not completely dismissed either. It sits in that space where it's just convincing enough to keep people interested, but not strong enough to be accepted. And that uncertainty pushes the focus back to the source of the idea itself. Because if the machines are difficult to verify, then the next question becomes whether the patterns they came from were ever as precise and meaningful as Baudo believed in the first place. Crop circles. Before going further with Baudo's machines, it's necessary to separate what's documented from what's assumed. Crop circles have been studied for decades, and not all of them fall into the same category. The simplest fact is this: many crop circles are confirmed hoaxes. In the early 1990s, two men from England, Doug Bower and Dave Chorley, publicly demonstrated how they created formations using wooden planks, rope, and careful planning. They showed that large, clean-looking circles could be made overnight without advanced tools. Their confession explained a significant portion of the early formations and set a baseline. Humans are fully capable of making convincing patterns in fields. But that explanation doesn't cover everything. As crop circles became more complex in the late 1990s and early 2000s, researchers began documenting formations that included features harder to dismiss so easily. Some patterns contained hundreds of individual circles arranged with consistent spacing across large areas. Others incorporated geometric relationships that matched known mathematical constants like pi and the golden ratio with a level of precision that required careful measurement. In some cases, investigators reported physical changes inside the formations themselves. Plants were bent close to the ground without snapping, which is unusual because a broken stem is the expected result when force is applied mechanically. Some studies suggested that the nodes, the joints in the plant stems, had expanded, as if they had been exposed to a brief burst of heat from within rather than being crushed from the outside. Soil samples from certain formations also showed differences in magnetic particle alignment compared to surrounding areas. These changes aren't present in every crop circle, but they've been reported often enough to keep the debate active. That said, none of these observations point directly to a single explanation. There is no confirmed evidence that crop circles are created by extraterrestrial intelligence. There is also no single natural mechanism that fully explains every formation. What exists instead is a mix of confirmed human-made patterns, unexplained anomalies, and a large amount of speculation layered on top. This is where Baudo's interpretation becomes important. He didn't claim that every crop circle was meaningful. He believed most of them were either hoaxes or noise. What he focused on were the formations that shared specific structural features, repeating ratios, off-center circles, and layouts that could be translated into mechanical systems. The problem is that identifying which formations are authentic isn't straightforward. Different researchers use different criteria. Some rely on physical characteristics like plant bending and soil composition. Others focus on geometric complexity. There is no universally accepted standard that separates genuine anomalies from well-executed human designs. That uncertainty affects everything built on top of it. If the source material is inconsistent, then any system derived from it becomes harder to verify. A pattern that looks precise could be intentional engineering, or it could be the result of a skilled group of people working with a design plan. From a distance, both can look identical. This doesn't invalidate Baudo's work, but it changes how it has to be interpreted. Instead of starting with the assumption that crop circles contain information, the safer approach is to treat them as patterns first and test whether those patterns produce consistent mechanical results. And that brings the story to its final point. Because once you account for what we actually know and what we don't, the entire claim comes down to a limited set of possibilities. 3 possibilities. After everything Baudo claimed, everything he built, and everything we actually know about crop circles, the story doesn't end with a single answer. It narrows down to a small set of possibilities, and each one leads to a very different conclusion. The first possibility is the simplest. Baudo was wrong, not in the sense that he fabricated everything, but in the sense that he misinterpreted what he was seeing. The patterns he studied may look structured, but that doesn't mean they were ever meant to function as machines. When he translated those patterns into mechanical systems, the behavior he observed could be explained by known principles: imbalanced rotation, stored energy in springs, and measurement limitations. Under this explanation, the machines don't produce extra energy. They just create the appearance of it under certain conditions. And if that's the case, then the entire idea of crop circles as blueprints collapses into something much more ordinary, a mix of human-made designs and natural variation, interpreted through the lens of expectation. The second possibility is more uncomfortable. The machines do something real, but not what Baudo thought. It's possible that his designs revealed a configuration that is unusually efficient, not a violation of physics, but a system that reduces energy loss more effectively than typical machines. That would explain the low heat output, the sustained motion, and the unusual behavior at higher speeds without requiring a new source of energy. In this case, the breakthrough isn't free energy, it's optimization. That still matters. A system that dramatically improves efficiency could change how energy is generated and used, even if it doesn't eliminate the need for input entirely. But it also means the connection to crop circles might be coincidental. The patterns may have inspired the design, but they wouldn't be the source of the underlying physics. Then there's the third possibility. Baudo found something that hasn't been fully understood yet. Not necessarily alien technology and not necessarily a complete rewrite of physics, but a system that interacts with forces or conditions that aren't fully accounted for in standard models. If that's true, then the lack of replication becomes more complicated. It wouldn't just be about building the same machine, it would be about recreating the exact conditions that make the system behave the way it does. That's the only scenario where his original claim holds weight. Because for the idea to be true, two things have to happen at the same time. The patterns have to encode functional information, and the machines built from those patterns have to produce results that can't be explained by existing models. So far, neither has been proven in a way that others can independently verify. Until someone builds one of these systems, measures it under safe conditions, and shows exactly where the extra energy comes from. The idea sits in that space between possibility and error.